What if I told you that the secret recipe for your smartphone, your Wi-Fi, pretty much the entire electrical grid is hidden inside a government exam guide? Well, today we're going to crack open the FCC's technical manual to uncover the fundamental rules that literally power our world. And trust me, this isn't a test. It's the blueprint for modern life. So, we're going to take this list of what looks like just a bunch of random rules, and we're going to turn it into a story. It's a story about how we build technology, starting from a single spark of an idea all the way to a signal that can travel around the globe. And, like learning any new language, it all starts with the basic vocabulary. Every single field has its core vocabulary, right? Well, in electronics, it all kicks off with how we measure power and energy. Once you really get a feel for these fundamental units, I promise, everything else just starts to click into place. Okay, let's start with a word you see everywhere, the watt. You see it on a light bulb, a 60-watt bulb. That number isn't telling you how much energy is in there, it's telling you how fast it's using the energy. A watt is all about the rate of flow. Think of it as the speed of the energy. So if a watt is the flow, then what's the actual stuff that's flowing? Well, that's the joule. The joule is the actual amount of energy. Here's a great way to think about it. A joule is like one bucket of water. A watt is just the measure of how fast you're pouring that bucket. So 1 watt is simply 1 joule, 1 bucket, being used every single second. Now, here's where it gets interesting. Circuits can be a little bit deceptive. I want you to think about a big glass of beer. The total volume, foam and all, is the apparent power. It's what the circuit looks like it's drawing. But the actual beer, the part you can drink, that's the true power, the part that's doing the real work. The foam is just wasted energy. And for engineers, the whole game is about minimizing that foam to build more efficient stuff. All right, now that we have the basic language down, let's dive into the invisible forces that are at play here. We're going to look at the fundamental principles that make everything tick and the specific materials we use to control them. This, right here, is one of the most fundamental relationships in all of physics. I mean it. Electricity and magnetism are basically two sides of the same coin. Anytime you push an electric current through a wire, you create a magnetic field around it. It's that simple. And that one principle is the engine behind electric motors, generators, transformers, pretty much everything. And nature has this really interesting quirk. It resists change. It always pushes back. So when you push current through a coil to create a magnetic field, Lenz's law says that field is going to push right back at you, creating a little voltage that opposes what you're doing. It really is like electrical inertia, a force that just tries to keep everything exactly as it is. So how do we actually manage all this flow? Well, it all comes down to choosing the right materials. On one hand, you have conductors like copper that are just jam-packed with free electrons that are itching to move. On the other, you've got insulators like mica or rubber that hold onto their electrons for dear life, stopping the flow cold. Oh, and here's a weird one. At really high frequencies, the current actually avoids the center of the wire and only travels on its surface or its skin. Okay, we understand the forces, we've got the materials, now we can actually start to build. These are the Lego bricks of electronics, the essential components we use to store, resist, and control the flow of energy in really precise ways. First up is the capacitor. Its whole job is just to store electrical energy in an electric field. The best way to picture it is like a tiny, ultra-fast rechargeable battery. It can charge up and discharge in a fraction of a second, which makes it perfect for things like smoothing out power or creating timed circuits. Then you have the inductor, which is kind of the capacitor's counterpart. Instead of an electric field, it stores energy in a magnetic field. And it acts a lot more like a heavy flywheel. It absolutely hates changes in current. It will fight any attempt to start, stop, or even just change the flow of electricity that's going through it. So what you have here is this perfect duo. The capacitor opposes any change in voltage, while the inductor opposes any change in current. They're complete opposites, but when you put them together, they can trade energy back and forth, from the electric field to the magnetic field. And that dance they do forms the basis of the filters that tune our radios and the oscillators that create the signals in the first place. So, if capacitors and inductors are the building blocks, the transistor, that's the spark of intelligence. It is the absolute game changer. It's a microscopic switch with no moving parts. And by turning on and off billions of times a second, it can do two magical things. It can amplify a tiny signal into a really powerful one, and it can create these simple yes or no decisions that are the foundation of all digital logic. Every single computer, every smartphone exists because of this one invention. Okay, this is where it all comes together. We're going to combine these building blocks in some pretty clever ways to create circuits that don't just move electricity around, they can actually process information, make decisions, and even remember things. We're about to build a brain. But before we can build, we need to know the first rule of circuit analysis, Ohm's law. It's this simple, elegant formula that tells us exactly how voltage, current, and resistance are all connected. If you know any two of them, you can always find the third. It's the mathematical foundation for pretty much any circuit you can think of. Remember those transistors? When we start combining them, we create these things called logic gates. This here is an AND gate, and it's a fundamental decision maker. Just think of it like a security checkpoint that needs two keys at the same time. It will only produce a true or a 1 at its output if input A and input B are both 1. Otherwise, the output is 0. And as you can see from this truth table, its behavior is perfectly predictable. The only way you're getting a 1 on the output is if you have a 1 on both inputs. This absolute, unwavering logic is the bedrock of all digital computing. It's how we build everything from a simple calculator to a supercomputer, one simple, lightning-fast decision at a time. Now, the flip-flop takes that logic one giant step further. By arranging these logic gates in a special feedback loop, we create a circuit that can actually remember a state. It can be set to either a 1 or a 0, and it will hold on to that value until a new signal tells it to change. This is it, the simplest possible form of computer memory, a single bit. So now we can assemble everything we've learned from the basic units to the logic gates and really understand the magic of radio communication. It's all the same principles we've just talked about, just applied on a much grander scale to send information right through the air. You know, a radio receiver is an incredible system. It starts by grabbing a super faint signal from the air and giving it a boost with something called an RF amplifier. Then a mixer comes in and shifts that signal down to a lower, easier-to-manage frequency. After that, the IF amplifier provides most of the muscle, the amplification and filtering. And finally, the detector's job is to recover the original voice or data from that signal. Now, on the other side, in the transmitter, you need different kinds of amplifiers for different jobs. We call these classes. A Class A amplifier, for example, is incredibly accurate. It gives you a perfect copy of the signal, but it wastes a ton of power. Then you have Class C, which is super efficient, but not very accurate. So it's always a trade-off between getting perfect signal reproduction, which we call linearity, and being efficient with your power. And finally, how do we actually get our voice onto that radio wave? Well, that whole process is called modulation. A balanced modulator is this really clever circuit that takes your audio signal and a radio frequency, mixes them together, and then does something amazing. It gets rid of the original carrier wave, leaving just the information we actually want to send. And there you have it. We went from the simple language of watts and joules, through invisible forces and logic gates, all the way to a functioning radio. You see, these aren't just abstract rules in a textbook. They are the fundamental principles that power our entire modern world. The only thing that ever really changes is the scale. Thanks for watching.